How can we look not just inside an atom, but inside what atoms themselves are made of? And what are fundamental building blocks from which planets, stars, us, and everything in the universe are made, excluding, of course, things like dark matter? As science developed, our understanding of the universe expanded across different scales. At one time, we thought that the solar system was practically all that existed, even its structure was misunderstood. Later, we thought that our galaxy was the entire universe. Now we know that the observable universe is enormous and consists of hundreds of billions of galaxies, and the universe as a whole may even be infinite. And don't get me started on the multiverse. Something similar happened with our understanding of the microworld. At one time, it was believed that all matter consisted of the smallest indivisible particles, atoms. Then, after a series of discoveries, we arrived at a picture in which the atom has a nucleus made up of protons and neutrons with electrons around it. It seemed that there was nowhere smaller to go, but in the 20th century, quarks were discovered, from which protons, neutrons, and some other particles are made. Of course, it's a bit more complicated than that, but overall, together with electrons, quarks are the smallest fundamental particles that make up all the ordinary matter we're familiar with. There are also gluons, but we'll talk about them later. But what if this is just another stage, and later it will turn out that quarks themselves are made of something? It may turn out to be so, but so far it hasn't. There is also another interesting question which I briefly mentioned in my recent video about virtual particles. And I don't think that any scientist doubts that quarks exist. But there is a small catch. No one has ever directly seen individual free quarks. So why is everyone so confident that they exist? It often happens that we can obtain quite strong evidence for the existence of something without any direct observation, and the story of how this evidence was obtained can be very interesting. Today we'll talk about how and why quarks were first predicted and then discovered, and what they actually are, about the first moments of the universe, quark stars, and also could quarks themselves be made of something else? I'm Andrei, and this is Cosmos Elementary. The modern view of the structure of the atom is quite complicated. Moreover, due to quantum effects, electrons are not little balls orbiting the nucleus, but rather electron shells or clouds, where we can only talk about the probability of where the electrons might be. And inside protons and neutrons, there are different types of quarks, held together by the strong force or by gluons. On top of that, there are all sorts of effects with virtual particles, which we discussed separately recently, but today we are primarily interested in quarks. And how can we detect them? Naively, one might think that you could just take a more powerful microscope, but if only it were that simple. It's clear that ordinary optical microscopes won't work here. Their useful magnification is limited to roughly 1,000 times. The diffraction limit gets in the way here, along with the relatively large wavelengths of visible light. But if instead of light we use a beam of electrons, whose wavelengths are much smaller, we can achieve magnifications of 1,000,000 times or more. Today there are many microscope technologies, various types of electron microscopes, scanning, tunneling microscopes, and so on. And I think it won't be news to many of you that modern microscopes allow us, in a sense, to see not only cells and molecules, but even atoms. Moreover, scientists have been obtaining images of atoms for decades now. Many of you will probably remember the famous animation A Boy and His Atom, created at IBM's laboratory. However, here we're not exactly seeing individual atoms, but carbon monoxide molecules, each of which consists of 2 atoms, 1 carbon and 1 oxygen. You can find many images of atomic crystal lattices obtained using powerful microscopes. Here's another fairly recent image where individual atoms can be seen. Or here is a single atom. And not long ago, scientists even managed to capture an image, well, of course, not of a single electron, but of the electron cloud in a hydrogen atom. But beyond that, actually seeing the subatomic particles themselves is a major challenge, both because of quantum effects and because they're simply incredibly small. In such images, it may seem that quarks aren't much smaller than protons, but as it is often the case with scientific illustrations, their purpose is to convey the concept, and it's difficult to represent the actual scale accurately. In reality, we don't know the exact size of quarks, and they could be thousands of times smaller than protons. This can be confusing, but again, in practice, everything is trickier than it appears in illustrations. And a proton isn't just 3 quarks. That's not all. Particles are disturbances and fields and all that. Well, in short, today there are no microscopes capable of seeing objects this small, and it's not even certain that it will ever be possible to do so directly. And yet somehow the existence of quarks was already discovered back in the 1960s. The story behind this is quite tricky. Today we know a whole bunch of subatomic particles, both elementary and composite. But less than 100 years ago, in the 1930s, the situation was completely different. The electron was known, the proton was discovered, and shortly after the neutron. And then there were a few other particles, like the positron. At the same time, there was a mystery how protons in the atomic nucleus stay together instead of flying apart. After all, they all have the same positive charge. And we know that they should repel each other. So there must be some force holding them together. A very strong force. The strong force. Today we have some understanding of how it works, but back then we didn't. In 1935, the Japanese physicist Hideki Yukawa predicted the existence of the pion. It was predicted that these particles could hold atomic nuclei together. In 1947, the pion or pi meson was discovered. Hideki Yukawa received the Nobel Prize in Physics for developing the meson theory, becoming the first Japanese theoretical physicist to be awarded this prize. As Jerome Isaac Friedman, another Nobel Prize winner whose work made a significant contribution to the discovery of quarks, writes in his article, when the pion was discovered, there was great excitement in the physics community because it seemed that with the discovery of a new particle, a deeper understanding of the subatomic world was beginning to take shape. However, that feeling didn't last long. It turned out that the pion had a different role. Now we know that this role is carried out by other particles, gluons. But scientists kept discovering more particles. First one, then another, then the 10th, the 20th, more pions, kaons, and other hadrons. At the time, all of them seemed like fundamental elementary subatomic particles. This whole collection was called the particle zoo. And instead of gaining understanding and a simple picture, things actually became much more complicated. There was a whole bunch of particles. It wasn't clear what some of them did, how they were connected, and most importantly, it was impossible to describe them all within a single coherent theory. But in the early 60s, an interesting scheme for classifying all these particles began to emerge. Two scientists, Nobel laureate Murray Gell-Mann and Yuval Ne'eman, independently proposed this classification. Particles have various properties such as mass, charge, and spin. They proposed a system in which particles with the same spin were treated as different states of a single entity. Particles with spin 0, such as pions and kaons, form a meson octet, meaning that there are 8 particles. Another group with spin 1.5 forms a baryon octet. This grouping of 8 particles is called the eightfold way. With spin 3/2 forms a decuplet of 10 particles. In fact, Gell-Mann and Ne'eman did for physics what Mendeleev did for chemistry with his periodic table. But here we don't have just one table, we have several groups. This kind of classification not only helped bring order to the particle zoo, but also allowed scientists to predict new particles that were later discovered. The question is, why was this scheme so successful? Could there be a deeper underlying mechanism behind these patterns? Soon such a mechanism was proposed, and this is where quarks enter the scene. As the basis for the entire classification of dozens of particles, one simple idea was proposed. Perhaps all these particles are not fundamental, but are themselves made of smaller parts. The whole particle zoo is just different combinations of 3 particles and their antiparticles. The idea was again independently and almost simultaneously proposed by 2 scientists, the aforementioned Murray Gell-Mann and also George Zweig. They called these hypothetical particles by different names. Gell-Mann called them quarks, but the word was not invented by him. He took it from James Joyce's experimental novel Finnegan's Wake. The novel contained many words invented by the author, and the word quark was one of them. Zweig, on the other hand, called them ace. That is, the ace like in playing cards. Obviously, Gell-Mann's name stuck, and today we know these particles as quarks. But as you may have noticed, this still can't be called the discovery of quarks, the smaller components of subatomic particles. At this stage, it was only a hypothesis, and most scientists didn't like this hypothesis very much, especially because it had one very big problem: the problem of fractional charge. What is that? I think everyone has heard about electric charge in general. It's a property of matter, or more precisely of elementary particles, that governs how matter interacts with electric and magnetic fields. And everyone knows that charge can be positive or negative. Plus, minus, that sort of thing. An electron has a negative charge, a proton has a positive charge, and a neutron is neutral with no charge. Now let's take a look at the other particles. Let's take a look at the modern standard model. And for now, I've intentionally left out the quarks. Here, for each particle, 3 properties are shown: mass, charge, and spin. The charge is the second one from the top. Here are the particles with a negative charge, -1. Here are the neutral ones, their charge is 0. The W boson is labeled +-1, since it can be either positively or negatively charged. Now let's look at a few more particles that aren't included in this table, since they are composite particles. The proton has a charge of +1, and the neutron accordingly 0. The previously mentioned pions come in different types, with charges of +1, -1, and 0. And we can keep going. Any subatomic particle we take, aside from quarks, is either neutral with 0 charge or has a charge of +1 or -1. That was also the case at the time quarks were proposed. Even though atoms are made up of charged particles, except for neutrons, ordinary atoms themselves are electrically neutral. This is because the number of electrons equals the number of protons. Let's take a carbon atom as an example. It has 6 negatively charged electrons with a charge of -1 and 6 protons with a charge of +1. One balances the other, resulting in 0 net charge. That is a neutral atom. As different isotopes of the same element have varying numbers of neutrons. But neutrons are neutral, and so they don't contribute to the charge anyway. And when atoms lose or gain an electron, they become charged: ions and cations. Now let's get back to the proton with its charge of +1. Has anyone noticed the problem yet, considering everything I just said? According to Gell-Mann and Zweig, the proton consists of 3 other particles. The charge of a larger particle is the sum of the charges of its constituents. So the sum of the charges of these 3 particles must equal 1. That is, for example, 1/3 plus 1/3 plus 1/3, or 2/3 plus 2/3 minus 1/3. It turns out that quarks can have a charge of +1/3 or -1/3, so a fractional charge. What kind of madness is that? But the real problem here isn't that a charge can be in principle fractional. And after all, what exactly is +1 or -1? One of what? One elementary electric charge. This is a fundamental physical constant, usually denoted by the letter E. It has a value which is measured, like all electric charge, in coulombs. And the value of the elementary electric charge is approximately 1.602 times 10 to the power of 19th coulombs. You can see the more precise value on the screen. Could this number be larger or smaller? Absolutely, why not? Initially, 3 types of quarks were proposed: the up or U quark with a charge of 2/3, the down or D quark with a charge of -1/3, and the strange or S quark also with a charge of -1/3, and also 3 corresponding antiparticles. And also let me remind you that these names, up, down, strange, and so on, don't carry any particular meaning. They're used for convenience. And quark theory suggests that a proton consists of 2 up quarks and 1 down quark. Adding the charges of 3 quarks, 2/3 plus 2/3 minus 1/3, we get a charge of +1, just like a proton. A neutron, which consists of 1 up quark and 2 down quarks, has 2/3 minus 1/3 minus 1/3, which equals 0. That is a neutral particle. The positively charged pion, which I mentioned, consists of 1 up quark and 1 down antiquark. Adding their charges, 2/3 plus 1/3, We get, unsurprisingly, 1. And this goes for any hadron you take. Whether it is a 3-quark baryon or a 2-quark meson, the situation is the same. The sum of the quark charges will be either +1, -1, or 0. It turns out to be a very elegant and coherent theory, which adds even more depth to these tables. But initially, the scientific community wasn't enthusiastic about the idea of quarks, precisely because at the time no subatomic particle with a fractional charge had been proven to exist. They tended to see quarks more as a mathematical trick than as something real. In short, it was necessary to search for and confirm the existence of such particles through experiments. By the early 1960s, experiments showed that protons and neutrons have a finite size, and that they are very small. At the same time, their structure appeared to be rather soft. This means that they aren't tiny, hard, impenetrable spheres. Rather, they have a diffuse or fuzzy, you could even say nebulous structure. We've already established that simply using a more powerful traditional microscope to see what's inside a proton is impossible even today, let alone back in the 1960s. But that doesn't mean that we can't try to, so to speak, probe the structure of the proton in another way, and that method was deep inelastic scattering experiments. To simplify it, here's the idea. You take a proton or a neutron and fire a beam of fast-moving electrons at it. These electrons, being smaller than protons, pass through them, possibly interacting in some way. On the other side, detectors record the electrons, measuring things like how they scatter and at what angles. When we get ordinary images, we're looking directly at the object itself. But in this case, we're more like looking at the pattern created by particles passing through the object. Right now, looking here, even without seeing the ball itself, we can tell that there are some smaller balls inside it. In real experiments, instead of light, we use electrons. So, of course, we don't literally see this kind of picture. Instead, we get data from detectors. There are other details too, but as a rough analogy, it works. In 1966, a new powerful linear particle accelerator was put into operation at Stanford. At that time, it was the most powerful instrument of this kind. Linear means it wasn't shaped like a ring, as in the famous Large Hadron Collider. Instead, the particles were accelerated along a straight line, 3.2 kilometers or about 2 miles long. By the way, it still remains the largest linear accelerator and almost the longest straight structure ever built. Along this straight line, electrons were accelerated, and at the end there were 2 experimental holes with detectors and other equipment. If you try to compare such a device to an ordinary microscope, it provided quote-unquote magnification over 60 million times greater. So we have such an instrument and we have 2 hypotheses, and we want to use this instrument to determine which one is correct. The first is the old hypothesis, according to which nucleons, that is protons and neutrons, have no internal constituents and are rather diffuse objects, and their electric charge is also in a sense spread out. In any case, we would expect that an electron moving at an enormous speed wouldn't interact with the proton in any significant way, but would simply pass right through it. The second hypothesis is the new one, according to which they have an internal structure made of quarks. In this case, an electron that occasionally flies inside will interact with its constituents, the quarks. It will scatter and be deflected at a large angle. And a large number of such electrons scattering at large angles would indicate the presence of components much smaller than the proton itself. But analyzing a large number of such scattered electrons, how exactly they were deflected and at what angles, it's possible to reconstruct the internal structure and get the idea of what the proton is made of. That is exactly what was done, and the experimental results supported the new model. They indicated that there is something inside the proton, and later the neutron as well, some very small objects. How small they were couldn't really be determined at the time. They were too small for the instrument to resolve their size, so the objects were called point-like. In fact, we still don't know the exact size of quarks. There are only some upper limits, such as the fact that they are at least 10,000 times smaller than a proton. So essentially it had already been shown that protons do consist of something smaller. But, as we know, this implies fractional charges. How can we prove that? This is already more difficult but not impossible. To learn something about the charge properties of these constituents, you can try using small particles with a different charge instead of electrons, and compare the results with the experiments using electrons. Here, scientists turn to neutrinos. The difficulty is that these particles interact weakly and rarely with ordinary matter. You may have heard that billions and billions of neutrinos are passing straight through you and you don't even notice it. A neutrino can fly through kilometers of iron and not even register that it was there. Nevertheless, experiments with neutrino scattering were carried out, and comparison with electron scattering confirmed the charges and showed that the quark model is correct. Quarks are not just a mathematical trick, they are real. But remember I said at the beginning that we haven't seen individual quarks. The key word here is individual. Quarks come in different types: blue, green, and red. Of course, this isn't literally about color as we usually understand it. Color refers to another quantum number, an additional property that quarks have alongside mass, charge, and spin. Color or color charge is somewhat analogous to the more familiar electric charge. In general, this property plays roughly the same role as charge does in electromagnetism. The difference is that color is related to the strong nuclear interaction, but instead of 2, plus and minus, we have 3 options here, conventionally called red, blue, and green, and for antiquarks, anti-red, anti-blue, and anti-green. Similar to electric charge, like colors repel and opposite colors attract, and they must also be conserved. In hadrons, the combination of the colors of their constituent particles must result in a net neutral color. And the phenomenon that prevents us from seeing individual quarks is related to color, the strong nuclear force, and gluons. Quarks which carry color charge are held together by the strong interaction, or more precisely by its mediators, the gluons. We talked in quite some detail about the fundamental interactions in my recent video on the fifth force. And the strong interaction is, as the name suggests, the strongest of the 4 forces that govern the universe. But in addition, it has another interesting property that sets it apart from gravity and electromagnetism. The farther apart 2 objects are in space, the weaker the gravitational attraction between them. The same goes for electromagnetism. But the strong interaction behaves differently. If we try to pull apart the particles held together by the strong force, like quarks, the force doesn't weaken. On the contrary, it actually increases. At some point, the energy becomes so great that it converts into a quark-antiquark pair, which then combines with the original quarks again. No matter how hard we try to separate quarks, confinement prevents it, and in the end, we still get hadrons made of quarks. Therefore, under normal conditions, individual free quarks cannot exist. In nature, they are always observed only as combinations of quarks, pairs, mesons, triplets, baryons. There can even be tetraquarks or pentaquarks, but never single isolated quarks. But there's one important caveat. They cannot exist independently under normal conditions. However, not everywhere or not always in the universe are conditions what we would call normal. If the conditions are extreme enough and the energy is very high, quarks can in principle exist outside of hadrons. The thing is, there aren't many such situations. First of all, this of course refers to the very first moments of the universe when it was incredibly dense and hot. Today it is believed that almost immediately after the beginning of the universe, for a few millionth of a second, the universe was in a state of quark-gluon plasma. During this brief moment, quarks, and in fact gluons, existed independently. However, it didn't last long. The universe expanded and cooled rapidly, and there was no longer enough energy for this, so quarks and gluons combined into hadrons. Interestingly, today in laboratories like CERN, on particle accelerators, scientists have learned to produce quark-gluon plasma for a brief moment. This requires an enormous temperature of trillions of degrees. Here too, we don't observe individual quarks directly. Rather, we detect the particles that form when the matter transitions to another state. However, by briefly studying the tracks of these particles, scientists can reconstruct what happened before that. Another possible place in the universe where individual quarks could exist right now is in hypothetical quark stars. This is a possible type of exotic neutron star in whose cores the temperature and pressure are so high that not only are atomic nuclei broken down into their constituent protons and neutrons, but the protons and neutrons themselves are further broken down into quarks. These would have to be special neutron stars teetering on the edge of becoming black holes. As I said, the existence of such stars hasn't been proven yet, but candidates for quark stars have been found. Too massive and too dense neutron stars that don't quite fit into current models. For example, in the gravitational wave event GW190425 detected by the LIGO and Virgo, which came from the merger of two neutron stars, and a quark star could have formed there. As we remember, originally 3 quarks were proposed, along with their anti-quarks. Today, however, 6 types of quarks are known. To the up, down, and strange quarks were added the charm, beauty, and top quarks, or C, B, and T quarks. The last one, the top quark, was discovered relatively recently in 1995. They differ in mass, and the top quark is the heaviest, about 61,000 times more massive than the up quark. But again, they decay quickly into less massive quarks, and we know of their existence only through the products of their decay. All of this together forms the elegant and coherent modern standard model of elementary particles, which describes many aspects of the universe very well and makes successful predictions that can be tested experimentally. We've come a long way from the chaotic particle zoo of the mid-20th century. But we still have one more question. Could quarks themselves be made of something even smaller? Why not continue the chain atoms, protons and neutrons, quarks? This cannot be ruled out, and there already exists a theoretical model describing such composite structures, not just of quarks, but of other particles in the standard model as well. These hypothetical particles are called Preons. There could also be several types of them, and different combinations would explain the varying properties of elementary particles, such as mass and charge. But so far there is no experimental evidence, neither direct nor indirect, for the existence of Preons. Perhaps future particle accelerators will shed some light on this, but for now, quarks and electrons are the smallest components from which everything we observe around us is made. Surely many will recall string theory, in which particles are considered as vibrations of incredibly tiny one-dimensional strings, but that's a different story, and once again there is currently no experimental evidence supporting string theory. But in the case of quarks, there is evidence. Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed the video, leave a like, comment and subscribe, and watch some of my older videos. They didn't get too many views, so maybe you will watch them and they will get some more views. Okay, I'm sorry. Thanks and goodbye.